Hey physics babies, welcome to the last lesson of the year, really. This is Unit 6, Lesson 5. Today we are talking about reflection, refraction, and Snell's Law. In Thursday's video, I'm going to do a quick formula sheet kind of guide. I think it'll be really helpful for you if you follow along and make your formula sheet, which I will let you use on your final exam. Look at that. Today I'm also posting a review packet. The review packet is optional. However, you know your review packet looks just like your final. I would complete it because if you prepare, you'll be successful on your test. All of this week, I'm available for questions regarding any of our lessons, any of the assessments that you want some help with, as well as that review packet. Next week is your final. So let's make sure we do some great things. Get out your notebooks and we'll get started. So by the end of the day today, you will be able to describe reflection and refraction of waves, as well as calculate the angle of refraction using Snell's law. So why is it that all of you, when you look into a mirror, can see your cute little faces reflected back at you? Reflection, right? So reflection is the bouncing of waves off a surface or medium. In the case of looking in a mirror, that surface is glass. But if you ever look at water, sometimes you can also see your reflection in water because the light waves bounce off the surface of the water and reflect back to you, just as a couple of examples. So definitely copy this diagram down. This is showing that reflection pattern. So we have light rays coming in. We call these our incident ray. The incident rays bounce off of a plane or mirror and are reflected back out. This line right here, this equal line, is called the normal. The normal is always going to be perpendicular to your surface. All right? So the key with reflection is that the angle of incidence, which is the angle between the normal and your incident ray, will equal the angle of reflection, which is the angle between the normal and your reflected ray. So if this angle right here is x, from here to here, this angle right here will also be x. Okay? And then remember, because this is 90 degrees, the angle of incidence plus whatever this angle down here is will add up to be 90 degrees. Okay. So this is part of why diamonds sparkle, right? Diamonds are an example of total internal reflection. A good diamond is, at least. All cut diamonds will shimmer and shine because of the angle that light is reflected in the diamond. The critical angle is about 25 degrees, and that critical angle means that the light comes in, the angle of incidence is 25 degrees when it hits this side right here. So then it reflects back out at an angle of 25 degrees. It hits this side, angle of incidence is 25, angle of reflection is 25, and it's able to bounce right back out the top of the diamond. When we cut diamonds too deep, instead of that light coming in and bouncing out the top, it bounces out the side. If we cut a diamond too shallow, instead it comes in and it bounces straight out of the diamond. So if we cut them too deep or too shallow, we don't get that internal reflection where the light comes in and bounces out, and that coming in and bouncing out of light is what makes it look really pretty and shine and sparkle and, you know, look like little rainbows. Just in case you were wondering. All right, so here's our first example. What is the angle of reflection if the angle of incidence is 35 degrees from the normal? So I'm saying that the angle of incidence is 35 degrees. We have to look at the directions our arrows are pointing, right? Because our angle of incidence is from our incident ray, which is the ray coming in to our surface. So here's our normal, completely perpendicular to our surface. And I'm saying that from here to here is 35 degrees. If this is 35 degrees, what's the angle of reflection going to be? It will also be 35 degrees. Remember, angle of incidence equals angle of reflection. Here's another one. We want to know what the angle of reflection is going to be given this angle below. So I'm saying with 42 degrees that this angle right here is 42 degrees. If we're going to find the angle of reflection, we first need to find the angle of incidence. Remember that our normal right here is perpendicular to our surface. So this adds up to be 90 degrees. If the whole thing is 90 and we have 42 degrees here, what's left over? We'll say 90 minus 42 equals what? 90 minus 42 is 48. So this piece right here is now 48 degrees, and that is our angle of incidence. If our angle of incidence is 48 degrees, what's the angle of reflection? Also 48 degrees. Pretty straightforward. Just make sure you look at the pieces you're given to ensure that you find the right piece of information for the answer to your question. All right, so why does a straw look like it's bent when you put it in a glass of water? Have you ever had a clear glass of water and you put something in it and you see it looks like it's going in and then all of a sudden it kind of is bent weird? This is called refraction. And here's an example of it. Refraction is the bending of a wave due to a change in medium or substance. So this change in medium changes the direction of the wave. So in this case, we've got we've got air, and then we have water. And as the light waves go from the water to the air, the light waves change direction ever so slightly. And that change in direction causes the image to look distorted. If you've ever been swimming and sometimes you kind of like look down, like your body is kind of at a weird angle, or if you look at someone else standing in the water, like top and then bottom, it's refraction. Kind of cool. So here we go. Here's our refraction. We have an incident ray. Remember, incident rays are our rays that are coming in. Here's our surface. We've got air on the top and water on the bottom, and we've got our normal. Down here is our refracted ray, okay? We've got some angle of incidence, and then we've got our angle of reflection down here. In refraction, your angle of incidence will not equal your angle of refraction, all right? They will be different because we're going through two different surfaces, or two different mediums. In reflection, it's only one medium that we're going through, right? If we look in the mirror, the light rays are only traveling through air. In this case, we've got air and then water. So this is part of how a prism will turn white light into all the colors of the visible light spectrum. So each color has its own angle of refraction, so the light bends a little differently, and that creates the rainbow. So looking back at our picture, our light ray comes in, it goes through the prism, and because each color of light has a different angle of refraction, they're able to be separated, all right? Red light has the smallest degree, and then violet light has the largest degree. Pretty cool. Here's another image that kind of shows us our angle of incidence right here versus our angle of refraction. Here's our normal. Remember, it's got to be perpendicular to the surface of where the substances meet. So this right here is a 90-degree angle. Okay. So we're going to practice. We're going to label our incident ray, our refracted ray, our normal, the angle of incidence, and the angle of refraction. Definitely copy this diagram down because it'll help you. So our incident ray is right here. I'm actually going to kind of label these with numbers so that way you don't have to see so much of my chicken scratch. 2, 3, 4, and 5. That's still really bad. All right, our incident ray is the light ray that's going in. Look at the direction your arrows are pointing. Here we go. Because my arrow is pointing down, so I know that this has to be my first ray. All right, my refracted ray is the other ray, right? 2. It is coming from my incident ray, and it's continuing to point out and down. Remember that these rays are connected. All right, my normal, it has to be perpendicular to the surface. So my surface where my two mediums are meeting, perpendicular is right here. So this is my normal. All right, angle of incidence is from the normal to the incident ray. So this angle right here is my angle of incidence. My angle of refraction is from my normal to my refracted ray right here. And there we go. Make sure you take a second, pause this, get that written down. All right, we're going to do the same thing. We're going to label our incident rays, our refracted rays, and then our angles. And we're just going to do it for one of these lines. So I'm going to do the red one. Right. My angle of incidence, one is right here. My refracted ray, two, is right here. If I draw a normal, it's got to be perpendicular to my surface, 3. My angle of incidence, 4. And then my angle of refraction, 5. Every time, though, that you have a ray going from one surface to another, you get this refraction. So we've got it once right here, but then it happens again down here. All right, so I'm going to draw it again, but this time I'm going to use our blue line, and I'm going to change this color so maybe we can see it a little bit better. So my incident ray coming in is right here, 1. My refracted ray is what's coming out, 2. My normal is perpendicular to this meeting of the glass and the air, right, between the two substances. So perpendicular, there's my normal, 3. Angle of incidence is between the normal and the incident ray, right here, 4. My angle of refraction is between my normal and my refracted ray, right here, 5. So every time a light wave passes from one medium to another, you get refraction. And that means if I have one single light ray going in between a bunch of different mediums, we have a bunch of different incidences of refraction. Okay. So let's talk. We already talked about this, it's refraction. All right, what is this picture an example of? This is also an example of refraction. So here is where the fishy actually is. Oh no, I'm sorry. Here's where the fish actually is, but due to refraction, this is where the fish will appear to be. How about this one? What's this an example of? Take a second, think about it. This is an example of reflection. My light ray comes in and it bounces off of this surface to be seen again over here. If the ray is able to travel through the surface, and then we'd see it coming out down here, that would be an example of refraction. But because it's actually bouncing off, this is reflection. All right, what's this an example of? Here we actually have two things happening, right? We've got reflection right here. Oh, sorry. We've got reflection right here up at the top because the light wave comes in and bounces back out. But we also have an example of refraction because some of the light waves come in and travel through the medium and is refracted down here. Okay. So index of refraction is called N. The index of refraction, N, is a constant and it's associated to a specific material. So all materials have their own specific index of refraction. I will always provide you with an index of refraction, but you need to know that they are specific to each material and that they do not have any units. So the higher an N value is, the more the light will bend and slow down. To find an index of refraction, we take C, which is the speed of light, 3 times 10 to the 8 meters per second, and divide it by the velocity of the wave in that material. So whatever the speed of light is in a vacuum, we divide it by the speed of light traveling through whatever that material or medium is to find that material's index of refraction. Take a second, make sure you copy down this formula. So here are some examples. In a vacuum, the index of refraction is 1.0. In air, our index of refraction is 1.00029. A very slight difference, but that means that light rays travel a little bit slower in air than they do in a vacuum. Over here, if we look at water, we can see that water has an index of refraction of 1.33. So do light waves travel faster or slower in water than they do in air? they travel slower. This is a higher index of refraction. So that means that the light is bent more and will travel slower than it does in air. Okay, keep going. So we're going to do an example. A physicist measures the speed of an electromagnetic wave, or maybe just a light wave, as 2.6 times 10 to the 8 meters per second. We want to know what the index of refraction of the medium is. So we know the velocity of this wave is 2.6 times 10 to the 8 meters per second. We want to know the index of refraction. So I'm going to use N equals C over V. N will equal C, which is 3.0 times 10 to the 8, and we will divide that by 2.6 times 10 to the 8. Use your calculator. And I'm getting 1.15 as our index of refraction. There are no units on index of refraction, so we are actually completely done just like that. Remember to round to 3 sig figs with all of your answer choices. All right, moving into Snell's Law. Snell's Law is a relationship between the angles of incidence and the angles of refraction between the two media. So N1 times sine theta 1 equals N2 times sine theta 2. N1 is your index of refraction for the first medium. Theta 1 is your angle of incidence. N2 is the index of refraction for your second medium. And theta 2 is your angle of refraction. We're about to get to the part where it's really important that your calculator is in degree mode. I am giving you degrees. Make sure your calculator is in degree mode. If you are using that calculator on your phones, you need to hit the mode button and just make sure that degree is highlighted, okay? It'll save you a lot of headaches and sadness later on, I promise. So remember though that the N of the material goes with the angle in that material. So here we go. We've got light traveling from air to a region of lead, making an angle of 40 degrees. The first thing we're going to do is calculate the angle of refraction. So this angle that I provided, 40 degrees, is my angle of incidence. I'm going to call it angle 1 because angle 1 is my angle of incidence. We're traveling from air to lead. So this is my first substance. This is my second substance. So figuring out my givens, I'm going to write N1 equals 1.0 because air, right, is my first medium. The N for air is 1.0. Technically 1.00029, 1.0 is good enough for me for this problem. Again, notice I'm providing it for you in the problem, okay? My angle of incidence, my theta 1, equals 40 degrees. And then N2 equals 2.6. So we're going to plug all this into N1 sine, theta 1, which will equal N2 sine theta 2. So 1.0 times sine of 40 degrees equals N2, which is 2.6 times the sine of theta 2. Remember, theta 2 is my angle of refraction. That's what I'm looking for. So in your calculator, let's get a number here. 1.0 times the sine of 40. You're going to get a long decimal. Leave the long decimal in your calculator, but shorten it on your paper. So it's 0.642. I'm just going to take 3 numbers from it, but really it's 0.64278766097. and probably keeps going. I'm going to leave that whole number in my calculator, but I'm just going to shorten it right here so we don't have to write that whole big long number out. Time equals 2.6 sine of theta 2. I'm just bringing down the rest of my values. Now, we need to get sine of theta by itself so I can get theta by itself. I'm going to say what operations happen between this 2.6 and the sine? Multiplication. So we're going to undo that with some division. I'm going to divide both sides by 2.6. In my calculator where I've got this big long number, I'm just going to hit divide by 2.6. All right, I'm getting another long number. That's okay. I'm going to leave it in my calculator and just abbreviate it right here. 0.247. In reality, it keeps going, but that equals the sine of theta 2. Now, how do we undo sine? We use inverse sine. So on your calculator, you have a calculator, you look at the sine button, and you see in yellow on mine it says sine to the -1. That's your inverse sine. If you were using your telefono calculadora, same thing, right? There's the sine button, and then above it is that sine -1. So you will hit second. That's activating all of those other colors, right? So on my calculator, that activates the yellow. On the phone, hitting second activates the blue stuff. And we will hit second sine to get sine -1. All right, see? Second, I hit the sine button and I get sine -1. Whatever we do to one side, sorry, we got to do the other. Because inverse sine and sine cancel out, and I'm left with theta all by itself. And so I've got sine -1. I need to get this number in there. So I'm going to type second answer. And like for me, that's that little minus sign. On your phone calculator, it would be the same thing. You'll type second and then the little negative symbol, and that will put in to your inverse sine the number that you got above. When you do that, sine inverse of 0.247226037, you should get 14.3. 14.3 as your theta value. If you struggled with that, it's okay. Come to office hours and I'm happy to work it out with you, okay? All right. We have one more problem we have to do. We have to determine how fast the light will be traveling in the LED. So I'm about to clear all this. Make sure you pause me and get it copied down. All right, so how fast is the light going to be traveling in the LED? This is going back to N equals C over V. Remember, the N for the LED is equal to 2.6. So we're going to say 2.6 equals 3.0 times 10 to the 8 divided by V. If I want to get V by itself, I first have to get it out of the denominator of my fraction. So to get it out of the basement, we are going to start by undoing division, which is multiplication by V. Whatever we do to one side, we got to do to the other. So now I've got V times 2.6 equals 3.0 times 10 to the 8th. If I want to undo this times 2.6, we will divide both sides by 2.6, 2.6, and we can move to our calculator. I get that V equals, this is a big number, 1. So my calculator says 115384615. That's a big number. Here's what we're going to do. I'm going to write the first 3 numbers I see, rounding, right, if necessary. So I see 115, the next number is a 3. That 3 will just drop, and I'm just going to leave this as a 5. I'm going to put a decimal right here. And then on my calculator, I'm going to count how many spaces would I have to move my decimal to put it right behind that first number? I see 1, 2, 3, 4, 5, 6, 7, 8 times. So by putting a decimal here, I add times 10 to the 8th, and we have the same value. Add your units, because velocity has a unit of meters per second. And that's it. Again, pause it, copy it down. Come see me with questions. Oh man, we got a couple more examples. Okay, so an incident ray in air is approaching the boundary of an unknown material at an angle of incidence of 61.6 degrees. The angle of refraction is 41.4. We're going to determine the index of refraction of the unknown material. Okay, great. So N1 is 1.0 because the ray is starting in air. My angle of incidence, theta 1, is 61.6 degrees. The angle of refraction, that's theta 2, is 41.4. And we want the index of refraction, so we want N2. We're going to use N1 sine theta 1 equals N2 sine, oh my gosh, that was really bad, sine theta 2. Plugging in what we know, we've got 1.0 times the sine of 61.6 equals, I don't know what N2 is, so I'm just going to leave it as my variable, sine of 41.4. So the easiest way to do this is to plug all the numbers into your calculator in one shot. So I'm not going to plug this into my calculator yet. I'm just going to leave it there. And instead, I'm going to figure out how to move this whole piece away from N2 to get N2 by itself. So in between these two things, we have multiplication. How do we undo multiplication? Division. And whatever we do to one side, we got to do the other. So I'm going to divide both sides by sine of 41.4. 41.4. Those go away, and I'll have N2 all by itself. Here is where we'll go to our calculator. Remember my rule. Put everything in the numerator, if there's more than just one thing, in its own set of parentheses before hitting divided by, okay? My denominator just has one thing, so I'm not going to bother with parentheses. So I'm going to open a set of parentheses. I'm going to type 1.0 times sine of 61.6. Notice that I have two open parentheses, so I have to close my parentheses twice before I can move on, okay? Once I have those two parentheses closed, I can hit divided by sine of 41.4. Again, I've got one open parenthesis. I guess I will close it to be, you know, make sure I take care of all my bases, and then I can hit enter. I got that N2 equals 1.338. Okay, I say 3 sig fig, so let's see. This is my fourth number. It's an 8. So instead, I'm going to round this number up and then drop that. So my N equals 1.34. There are no units on index of refraction, so we are done. Next example. Right. We've got a light ray in air. It's approaching the boundary with glass at an angle of incidence of 35.2. We want to calculate the angle of refraction. So, oops. Last example at least. Hold on. N1 equals 1.0 theta 1, equals 32.5. And then N2 equals 1.52. we're using N1 sine theta 1 equals N2 sine theta, 2. Man, it's been a long time of me writing like this. You'd think I'd get better at it. Sorry. So plugging in our values that we know, 1.0 times the sine of 32.5 equals 1.52 times the sine of theta 2 that we are looking for. We want to know the angle of refraction, that's theta 2. So again, why don't we leave as much as possible alone and try and get theta all by itself first? The first thing we need to do is divide, right? Remember PEMDAS, we look for, when we're solving, we go in reverse, so we look for addition, subtraction, then we look for multiplication, division. So I see multiplication, I'm going to undo it with some division. 1.52 divided by 1.52. Those go away. I'm going to have that sine of theta 2 equals, I'm going to go to my calculator. So remember, put the numerator, if there's multiple things, in this case I've got the 1.0 and the sine of 32.5. So I'm going to put that in its own set of parentheses. Start my parentheses, 1.0 times sine of 32.5. Before I type my division, I'm going to count. I've got 1, 2 open parentheses. I need to make sure we close both of them. So close 1, close 2. Now I can do my division. Divided by 1.52. That is a big long number. I'm going to abbreviate it on my work page, but I'm going to use the whole number in a second in my calculator. So we get 0.358. Now, last step, we need to undo sine. We undo sine with inverse sine, so sine to the -1. Whatever we do to one side, we got to do to the other. These will go away. To undo sine, I'm going to type second sine. I've got the inverse. Now I want to call up my last answer. So I'm going to type second ANS for answer, and then we hit enter. I'm getting that theta 2 equals 20.98. Now, once again, 3 sig figs. So I count 1, 2, this is my third number. We look at the fourth. It is an 8. So I'm going to round up the next number and then drop this down. This is a 9. So that means rounding it up gives me, turns this 0 into a 1. But I don't want just 2 values, so I'm going to give it 0.0. So I still have 3 sig figs. Now, this is an angle, so I will say it's in degrees. When you are putting a theta into your answer for the assessment, make sure you actually type out the word degrees. So I would do 21.0, 1 space, degrees. Okay. Oh, look how beautiful that is. Perfection. All right. That is the last of our lesson. How crazy is that? So that's the end. End of our content for the year. That's all we're going to be able to get through. On Thursday, like I said, I'll do a formula sheet. The assignment that'll go along with that is for you to create your own formula sheet and just send me a picture of it so I can kind of make sure you're getting ready for that final. Finals are happening next week. Make sure you're coming to office hours, make sure you're doing your assessments, make sure you are reaching out with any questions or concerns that you have. You can get to me through email. You can make comments on your work. You can use my Google Voice number to call me or to text me. whatever you need. Just know that I love you lots and I'm thinking about all of you and I miss you like crazy. Have a great day and I'll talk to you soon. Bye.